Okay, so welcome everyone to our next talk in this online seminar series of the EDT community. You might have noticed, if we have a look at the schedule, that this is already the final talk of the second edition of our seminar talks, where today David McKee will give a will give a presentation. Before that, let me quickly do some advertisement also for the panel discussion that will take place in 2 weeks from now, where we were actually lucky to most probably have all of the presenters of this edition of the seminar series again for a 1 hour discussion and a 1 hour panel discussion. And after that, we will do some quick break and then most probably have another edition of this talk, of this online seminar series before summer. If you have missed any of the previous presentation, don't worry, you're also able to watch all of them on our website or on our YouTube channel. But let's focus on today's presentation given by David McKee. David has a lot of many years of experience already on building and developing large-scale digital twin solutions for many different domains, from aerospace to automotive and also smart cities. A couple of years ago, David also founded Slingshot Simulations, where he's now selling these digital twin solutions to their customers. And pretty much at the same time, he also joined the Royal Academy of Engineering as an enterprise fellow. And yeah, besides this practical experience, he also gave several lectures on digital twins at the University of Leeds and Oxford. And I think the part that will for today be most interesting for us is that David is also co-chair of the Digital Twin Consortium. And at the Digital Twin Consortium, he leads 2 different working groups where his work focuses on, roughly said, defining digital twins. So this is something I think that also in this community we have talked a lot about already. But David has actually managed to have the 300 organizations and companies who are part of the Digital Twin Consortium to agree on one definition on digital twins, and also agree on one reference architecture, how to implement these digital twins. And today he will present these results and also talk about open source solutions that are already available for parts of this reference architecture. So if you have any questions, I'm sure there will be a lot, you can post them in the chat or just raise them after David's presentation. But for now, I will hand over to you, David.
Thank you very much. And I would say good afternoon to most people. I always caveat as saying good morning or good evening, depending where people are in the world. So, looking forward to the conversation. So let me just start by sharing my screen, and hopefully that will come through nice and quickly. So could you just confirm that you can see my screen?
Yes, it works perfectly for me.
Brilliant. Okay, so thank you. Thanks for the introduction there. So as mentioned, I'm both the CEO and CTO at Slingshot Simulations, as well as co-chair of multiple working groups at the Digital Twin Consortium. I also lead their technology advisory committee, reviewing open source submissions within the OMG DTC. So I'm going to kind of go through a few different things and start with kind of a bit on kind of who I am and also a bit on the Digital Twin Consortium. So let me start with the Digital Twin Consortium itself. Some of you may be well familiar with this. So it's part of the object management group, and I'm sure you're all very familiar with OMG. And the DTC, being one of the 3 main constituent parts of it, has over 300 members now, industrial members, as well as research members, governments as well. I think we're over a dozen universities, multiple governments and cities as well, been part of this. And here's a snapshot of the membership, particularly these are the members that joined on day 1. I wish I had a client base so this long when I started Slingshot on day one, but clearly I didn't. And we see some of the most influential companies here in terms of who are leading the way, both in terms of setting standards, but also enabling the adoption of digital twin technology. And we can talk about digital twins, we can talk about systems integration, all of these wonderful topics from a research perspective. But when we look and try and realize these in the real world, it is the companies, particularly companies at the top of this list, who are the ones who are having the biggest impact and dominate the market. So, you know, and hopefully you'll be very familiar with these. Of these, when we talk about the reference architecture, which we'll come to in a moment, I'll particularly pull out that the reference architecture was co-designed, led by myself, but co-designed with Microsoft, Dell, Bentley, ANSYS, and Autodesk were the primary constituents here from the founding team, as well as a range of contributors from the rest of the membership, with, for example, Jitsu specializing in kind of the security aspect. There was Willow talking about it from a building perspective and more. So a very broad base here, contributing to the definition, and really in some ways enabled by the pandemic to allow more virtual meetings and actually speeding up this process. The process that went into this was a weekly meeting of the CTOs of each of these companies, meeting every week for between 2 and 4 hours to actually go through, debate, and argue about what do we mean by digital twin? What are the semantics, subtleties of words, subtleties of diagrams, even the subtlety of an arrow, which was painful at the time, but we've reached a great place. So as mentioned, I'm the CEO and CTO at Slingshot, and supported by a broad team. At Slingshot, we are 17 staff, having grown from a team of 3 people 2.5 years ago, and highly diverse with a lot of experience in the UK and US. Our background is as ex-academic, so at the University of Leeds primarily, and working on over $100 billion worth of research funding over a 20-year period in terms of realizing this type of solution and technologies, from data center thermodynamics to aircraft engines with Rolls-Royce, automotive with the likes of Jaguar Land Rover, and then working on multiple city projects as well. So let me start quickly by saying, well, what is a digital twin, and how have we defined that? And I'm going to build this up and kind of allude slightly to the methodology and the thinking that went through this process. And this is really important because understanding the definition that we agreed on between the 300 member companies really informs what had to be included within a reference architecture and what not. And particularly in terms of when we think about digital twin, what is a digital twin, but more importantly, what is not a digital twin? And that's a more contentious issue, but a really important one. So the core elements of a digital twin, we have a virtual representation, could be the model, could be the database, whatever tool you want to use it, but we deliberately picked around the wording here as virtual representation to not get us into specifically the worlds of modeling and simulation, because the term model has certain semantics that alludes to that is not necessarily appropriate for every digital twin. So the core element is a virtual representation, and then that has to be of something. It has to be of the real world. And a lot of the conversation around digital twins will allude to 3D models, to buildings, physical entities, physical things. Well, actually, that is also not necessarily appropriate. We see some great digital twin work, maybe of logistics processes. They're real world process, but they're not necessarily a physical thing. So actually allowing that space around entities and processes. And this kind of goes back to a lot of the work that we saw Michael Greaves do back in 2002, 2003 with the definition at NASA. And then probably from my perspective, the most important phrase in the whole definition of a digital twin is synchronization. The lack of synchronization in a system means that it will not be a digital twin. And this is a clear qualifying criteria, is that if your virtual representation is not synchronized with the real world in both directions, then it does not qualify. You could have the most amazing dashboard, the most amazing model, the most amazing simulation, but if it is not synchronized from the real world to instantiate that model or simulation with data, and if it is then not realized back into the real world through decision-making, could be through human decision-making, or it could be through operation technology, it does not qualify as a digital twin. It doesn't mean it doesn't have value, but it is not a digital twin. This was highly contentious. So you can imagine an awful lot of companies were ruled out from being able to describe their product as being a digital twin because it was just a dashboard, it was just a simulation. So that leaves us with a first sentence. A digital twin is a virtual representation of real world entities and processes synchronized at a specified frequency and fidelity. There's a lot of meat in that. And then that builds out that there are 3 subsequent sentences. So digital twin systems, they transform businesses by enabling understanding, by enabling decision-making and effective action. If they're not doing that, if they're not realizing the value of that synchronization back into the real world, it's not a digital twin. And we're particularly talking about digital twin systems here, and that's all about the maturity of these things. Actually, they have to be realized, built in IT/OT systems, and actually integrated with systems. The data or digital thread that there's a lot of conversation around at the moment is really important because you can't instantiate it without either real-time or historical data to then make decisions on top of. So digital twins use real-time and historical data to represent the past, present, and simulate predicted futures. And that's a really key element because you can't make the decision-making unless you're doing a level of prediction. So again, the agreement was that actually we're ruling a lot of companies out here because there's some great dashboarding technologies, some great analytics engines out there that will analyze real-time and historical data. Brilliant. However, the purpose of a digital twin is that forecasting element, that simulation element. And if it's not doing that, it is not a digital twin. And then you have to build these things. So they have to be built on IT and OT systems. They have to have a purpose to realize that value. They have to be integrated. They're built on data and so forth. So all of that allows us to get to the point where we can then design a reference architecture. And is there anything massively complex about it? No. However, it provides the guiding principles on top of which we can build. And I'm happy, by the time we do the panel session, there'll be a white paper that will be going out for publication by the DTC. So then I'm happy to share that with the group as well, which will look at how this reference architecture correlates with other standard architectures such as RAMI 4.0, with Industry 4.0, the Azure stack, the AWS stack, the IBM stack, and others. So there's a correlation, a big activity that has, in designing this, we've reviewed over a dozen standard architectures that are being proposed and adopted. So how does this work? What are the best practices that we can pull out from these? So the constituent parts can be summarized in this funnel. We have a virtual representation at the core. It runs on an IT or OT platform, so information technology and operational technology. Then in order to realize the value, there must be applications and services. These could, your different tools and so forth, could be dashboards, could be workflow engines, whatever it is. And then there is a level of service interfaces for integration and interoperability to enable that synchronization. And that, from a research standpoint, this continues to be the biggest area of research that the DTC is now continuing to focus. Having moved from our definition of virtual representation, having started to identify some of the key technologies and data formats for storage across different domains. And as an organization, we work across 8 different verticals. From natural resources, including environmental modeling, energy modeling, oil and gas, aerospace and defense, manufacturing, cities and transport, and so forth. Now focusing very much on that integration interoperability piece, particularly working with the IIC in terms of their standards around Industry 4.0 with things like OPC UA and so forth. So this provides the basis, and then we can put into this and build on top of this in terms of the different aspects. So we start with an IT/OT platform, and again, this will hopefully make sense, and it's hopefully fairly self-explanatory as we build through this. So we have an IT/OT platform, we have a virtual representation, we then have the real world. Well, that's a really important part that we can't forget. And we have the applications, and then we have the service interfaces wrapping around that. Very straightforward, but very, very important to understand. These are the base building blocks. Underpinning all of this are the traditional 5 pillars of security, trust, and governance. We can come to those in a moment. Your IT/OT platform is comprised of a relatively traditional cloud stack that we can decompose further from your compute aspect, your networking, your storage, your orchestration, your APIs, and your software tooling. This provides essential building blocks on top of which any digital twin system would have to be built. The virtual representation piece is, again, this the core, it's right at the heart of this, and it can be split into two primary representational parts. You have the computational aspect in which your simulations will sit, and you have your stored representations for your models. Now, you'll notice we are not using the word model. That is very important, as I alluded to at the beginning, because arguably you could easily use a spreadsheet here. Depending on the connotations, model may not be the appropriate term, and we spent months arguing about this particular piece. But you can break that down, and then underpinning that, you then have the modeling language, not model, the modeling language, and which is really important in terms of linking that loop, going from your stored representation, even if it's a spreadsheet, to understanding how do we realize value, how do we generate forecast simulations, and so forth. Then that's great. Well, but we need a synchronization mechanism. Great, we've got these interfaces, this level of integration, but we need to explore a mechanism to actually enable that interoperability, to enable that flow of data between the real world, the systems, the sensor systems. Even if that mechanism is a person on the street counting cars, which too often it is, that is still a mechanism for flowing data in one direction. The question is does it flow back in the other way? And the mechanism may be a different mechanism. And that's also important to realize, is that more often than not, your mechanism here will be different for the directionality of your data. Even if it's an IoT system, you have a sensor for collecting your data and you have an actuator doing something about it. It might be collecting traffic coming up to a junction, and then you're triggering your traffic lights based on some model. Now, more often than not, your traffic control systems are not running a digital twin, because they're literally running on, I see 10 cars, I'm busy, I'm going. There is nothing more to it. However, more and more, we are seeing, particularly in the US, more complex models looking at citywide planning of how do you respond to that, and running simulations. We're seeing particularly tools like Apache Sumo and MatSim and others being implemented within a systems of system perspective, live flows of data, to actually say, do we need to adjust our traffic flows in real time? We're seeing, particularly within synchronization mechanisms, technologies such as the OPC UA coming out of the OPC Foundation, and particularly working hand in hand with the RAMI 4.0 architecture as well, and particularly seeing Bosch and Microsoft leading that particular piece of work. Focus primarily on industrial automation, with the asset admin shell piece as well. All of those technology being open source and available to go and have a play with, and most people can probably get up and running with those particular technologies in probably half an hour in terms of a prototype. On the Digital Twin Consortium website, and I think I have a link to this at the end, there's actually a GitHub site, and there is a example with an asset admin shell example, as well as an example built using SysML, actually around how an espresso coffee machine works. Actually building that out in terms of an IoT interface from an industrial coffee machine, in terms of how is that interface linked within the manufacturing supply chain. And if the link isn't at the end of this, I will obviously share it afterwards, and I'll share it in the chat as well, so you can go and have a look. And all the code is all open source, as you would expect. From a synchronization perspective, there's two aspects to this. You have the ability to synchronize with the real world in terms of the data in and out, and those actuators and sensors, as we mentioned, or people in the loop, unfortunately. But you also have the level of data interoperability, because more often than not, there is a decoupling of these systems, whether it's for security concerns or whatever other reason might be there, or legacy systems. The simple fact is that actually that isn't a direct route through. So we need to look at data interoperability in terms of what other tools are in this chain, and how do we ensure that flow of data. It may be an SAP system in terms of maybe warehouse management. Well, actually, how do we link that in from a digital twin perspective? Well, we need to look at that from a data flows, and actually look at this from a systems of systems perspective. So with that being said, and this remains one of the biggest areas of challenge from a research perspective in terms of facilitating this, and it's also an area that we at Slingshot particularly focus on. You then need to wrap everything with just services. It's all about APIs. It's all about making it standard APIs absolutely everywhere. and preferably open APIs as well. And we do see, for example, there's many formats out there that are proprietary, closed source tools, closed APIs that are one of the biggest challenges to digital twin adoption and realizing digital twin systems is that a lot of the incumbent technology just isn't built to be open. It isn't built to be interoperable. And we're now seeing that those technologies need to be. So let me give an example there is, if you are doing emergency evacuation from a football stadium, well, the simulators that were built for managing that crowd piece were built to run on a single desktop, but they are the standard. They are when you go from a regulatory perspective, those are what are signed off in a planning process. They run on a single desktop. However, when we actually look at the world we now live in, where we have cameras, we have sensors, we have all this other information, we know where people are, we know what's going on. Actually, to make live decision-making, we need to integrate that within a wider system. But unfortunately, we can't use some of the traditional incumbent tools. So we either need to migrate those legacy solutions or adopt new solutions. However, those new solutions, the data hasn't been verified. And this is then the challenge that we then face, is how do we verify a new simulation platform, because we don't have 20 years of data that they were building on top of. And I've already alluded to, it's all about data. So underpinning this, those other data sources. Well, actually, you might be doing sensors on a vehicle. So you have your live data feeds with over-the-air updates from your Jaguar, your BMW, whatever. But actually, to provide you that context from a digital twin system perspective, there is other data that you need to take into account. So why are you getting information to tell you that the car temperature sensors are wrong? Well, why is it telling you that it's at -5 degrees? Well, actually correlate that with the weather. So the correlation of other data sources is really important to provide that overall context to inform better decision making. And then in order to realize that value from an application standpoint, there's a whole range of analytics and services. Traditionally, we're seeing most of the digital twin efforts at the moment are focusing on the 3D rendering. That is where most of the efforts is about that engagement through storytelling in terms of those, the pretty pictures. But actually, in terms of realizing the value in the decision making, that's only one small part of it. And I'd say it's less than 10% of it. It's a great picture, it's a great story, but it's all about the data flows going horizontally across this diagram rather than vertically. That's a really important thing, and we do see a lot of the community isn't quite getting that. They think it's a great picture, it's a great 3D model, it's a digital twin. No, it's a great model. It's a digital twin if there's data, it's going into it, and then you're using it for a purpose. If there's just data coming onto it, even better model, great. If you're not doing something with it, it's still not a digital twin. And that was really the key. Underpinning this, as I mentioned, we have the 5 key pillars, as particularly identified by the IIC in terms of privacy, security, safety, resilience, reliability. And can always point to a white paper, and that was published probably a couple of years ago, really outlining and breaking those down in terms of those elements. So that kind of gives you an overview in terms of all those elements, and I'll just kind of talk to a couple examples now in terms of that are being built within the DTC, and then a couple at Slingshot as well. So this is one that we're involved with, which is all about helping prevent deforestation. So in this case, this is an interesting hybrid between there being a level of manual data collection and live data collection from satellites. We have NGOs on the ground collecting information about what deforestation is happening, what plans are in place, and so forth. That is then all collated, fed in over 30 different data sources, all collated, analyzed in real time, in this case, and then fed to decision makers. And the decision-making process is not an automated one, because there's a lot more at stake than just, it's not an actuator. There's a buying process. So the process here, that feedback loop is actually a human loop, because there has to be the board level decision-making, which then realizes, go and buy this patch of land. And that's the thing that closes the loop in this particular case. So that it's an interesting example as a loop, and it's all about kind of solving that. Another example is looking at, again, 3D modeling in this case, but looking at the traffic data, helping in this case, in Leeds city centre, particularly helping them plan and respond and change their roadwork plans. So specifically saying, where are we currently directing traffic from the motorways to avoid roadworks? And the particular use case here is there was a particular problem around one of the core bridges in Leeds, and 18 months on from this project, it still remains a problem, because when a bridge is damaged, that is a very expensive problem, and also a major safety problem. So this was really focused around that, as well as a pollution problem, health concerns around the train station in central Leeds. We've worked across a broad range of other examples from data centers as well, in terms of real-time scheduling, and in terms of reducing the energy footprint of data centers, and as well as looking at atomic modeling as well. Although that one is working towards a digital twin. That is an example of where it's sitting at the modeling and simulation piece at the moment, in the theoretical space, and hasn't graduated yet, and probably won't for another who knows how long. But it kind of shows that maturity. In terms of going broader, these are kind of projects within the open source community at the Digital Twin Consortium. We see a big effort around this concept of treating buildings as batteries. So this is where we're looking at how within a building, particularly in the US, what capacity is there for storing energy? And can that ability to store energy and understand the distribution of energy as a fractal actually allow you to plan the energy production and energy supply in a more efficient manner? Because the energy loss is a significant cost in the system. And if you can more efficiently manage that, particularly as we see an increase in the amount of energy we need through electric vehicles primarily, we can become more efficient, and we can therefore have greater capacity without as big an investment. We still need a massive investment in infrastructure, but not as much. And this is very much about a real-time live system, and this is really focused around the Brooklyn Navy Yard in New York. We're seeing a similar concepts kind of being tested and piloted across 23 cities in the US, as well as looking at actually how do you use digital twins for prototyping different systems. This is all around energy planning, and a broad range of companies involved in just this one project. We then see this is work that's in Texas, looking at smart air mobility, 5G connectivity, autonomous vehicles, and looking at a whole systems of system perspective from a city. So actually, in this case, this is looking at building a digital twin system. Again, this will take a little while, but how do we plan for the build? What infrastructure do we need to put in place? And then once we put that infrastructure into place, how do we use a digital twin and integrate it to actually allow us to have that operational perspective? So this currently sits at the modeling and simulation level in terms of its maturity, and is currently evolving into a digital twin system. Here's another example that is open source, is now on GitHub as well, and this uses the Microsoft Digital Twin Definition Language, so DTDL, to define the parameters of it, and the whole model is there. And this is a nice, it's a semi-theoretical example. It's not of a given wind turbine, it's of a real wind turbine. Looking at how that works in terms of the data flowing to help you model and predict, and how to analyze and adjust how the wind turbine works. It's a great example of both taking sensor data from the turbine itself, as well as from other turbines, to take a system-to-system perspective, because as I'm sure you're all aware, you need to adjust those to the environmental conditions and the direction of the wind and so forth, or else you end up with a very expensive damaged wind turbine that you need to replace or maintain. So those give a sense and a broad range, excuse me, I'm drink water, of a range of examples within the DTC. And I'm going to go with actually one example. So I'm going to start with this example, just to give an example with the Rainforest Trust piece. I think it's a very important piece. So I'm going to go talk to this, briefly let you watch this, and then I'll finish with one quick video as well, just talking a bit about what Slingshot's doing and then we can have a bit of discussion around the reference architecture. So I will leave it there.
Making more impactful decisions is sort of the key point of it. But there's definitely such a realm of possibilities. It's quite exciting time to be looking into that.
Yeah. From a digital twin perspective, so if we're effectively creating a virtual digital copy of what exists in the physical world, right? So we help reduce the conflict so that we can plan better how we would tap into resources in those areas without causing large-scale destruction.
Taking that kind of data, mapping it, simulating it, looking for correlations between crime and deforestation is one of the big areas. Having a more in-depth picture of what is going on in these rainforests that's maybe not necessarily reported or clearly visible on the ground. We can take data sources that are a little bit more self-explanatory and make conclusions from those. That gives a really clear picture.
Giving that level of transparency, it can be shared and it can be given to the right authorities, or certainly the more eyeballs on these hotspots, the more pressure these local governments will have to start thinking about, okay, we've really got to protect these areas.
You could make an environment that was sort of conducive to the goals of all of these governments.
Yeah.
They would have high incentives to feed data into that, which would only improve a digital twin.
So I'm just going to finish with just an overview of Slingshot in terms of our platform, which is also freely available, particularly for researchers to use and have a play. But then we're always looking for feedback and opportunities for collaboration and saying, actually, I'd love it if we could do this with your platform, and we'd love to collaborate with any and all of you who are here today or listening later. So I'll finish with this, and then we'll go into some discussion.
Welcome to the world of limitless opportunity. Meet Compass Engine. Get ready to link, visualize, analyze, and simulate your data all in one place. No coding required. Your data drawn from an array of sources, ready to be explored. Upload your files. Brought together in a cloud data lake, which enables new insights to be fished out for your projects. With different doorways to intelligence open to you, are you ready to explore your dataverse? Bringing you your favorite tools and plugins that can be seamlessly accessed at any time. Our app ecosystem is here to enhance your productivity. Explore and discover data via the Compass map to visualize and analyze your new geospatial insights. Customizing and saving your findings for later. Do you want to discover hidden trends or reveal insights in seconds? Compass Analytics brings you an automated, user-friendly, no-code environment, allowing you to build analytics workflows in seconds. Your findings are now brought together for a clearer, bigger picture, presenting your insights and proudest findings in dashboards. Compass Engine is built with its growing community in mind. Collaborate on projects, share with other users, connect with the Compass Engine community. Your data has been on a journey. It is now intelligence ready, with a range of standard formats to use with your tools, optimized for continuing its journey into the intelligence metaverse.
So I will leave it there. and really open up to kind of any questions and so forth. So thank you.
Thank you very much, David. Let me, wait a second, let me give an actual physical applause. And also invite others to join me virtually or physically. I will stop